Dear students, in the last lecture we discussed the statement of Green's theorem. In this lecture we will try to verify the Green's theorem for a given integral. So the question is, verify Green's theorem, integral over C. The circle in the integral denotes it's a closed integral over C. That is, C is a closed curve. Closed integral over C, x minus 2y dx plus x dy, where C is the boundary of the circle or the region enclosed, region of the circular disk. X squared plus y squared is equal to 1. So before getting into the proof of the statement, let's write down the statement of Green's theorem. It states that integral over C f1 of x comma y dx plus f2 of x comma y dy is equal to double integral over R dou f2 by dou x minus dou f1 by dou y dx dy, where C is the boundary of the circular disk and R is the region enclosed by the boundary, that is the unit circle x square plus y square equal to 1. So in verifying the theorem, first let us take the LHS, that is left hand side of the theorem, that is the line integral over C f1 of x comma y dx plus f2 of x comma y dy. Okay, now this region can be split into two arcs, integral over C1 f1 dx plus f2 dy plus integral over C2 f1 dx plus f2 dy, where C1 is the part of the circle ACB and C2 is the we can say even the segment of or the sector of the circle, not even the sector, it's the part of the circle BDA. Of course they are the semicircle. ACB is the upper half of the circle and BDA is the lower half of the circle. So let's evaluate the integrals one by one. And before evaluating, since the region is circular, it will be convenient if we change the Cartesian system into polar coordinates. In polar coordinates we have x is equal to cos theta and y is equal to sin theta. Therefore by total derivative we have dx, x is cos theta, therefore dx is going to be minus sin theta d theta and dy is going to be cos theta d theta. So carrying over these substitutions, that is changing into polar coordinates the first integral, in the upper half of the semicircle it spreads over the first two quadrants. Therefore theta is the variable here. R, the radius of the circle, remain constant, therefore theta is the variable. In the first two quadrants we know that theta varies from 0 to pi. Therefore the integral reduces to integral 0 to pi. We can substitute cos theta in place of x, sin theta in place of y, and minus sin theta d theta in case of dx and cos theta d theta in case of dy. So making all the substitutions we can, and opening up the brackets, we get minus integral over 0 to 2 pi minus sin theta cos theta plus 2 sin square theta plus cos square theta d theta. And this could be further reduced using the trigonometric identities. Sin theta cos theta is nothing but sin 2 theta by 2, and this 2 sin square theta plus cos square theta can be reduced as split as sin square theta plus sin square theta plus cos square theta, and we know sin square theta plus cos square theta is 1. So the integrand becomes minus sin theta by 2 plus sin square theta plus 1 d theta. Because the integration is linear, we can go for term by term evaluation. So, and before we don't have the direct formula for sin square theta, again applying the identity, sin squared theta is 1 minus cos 2 theta by 2. Now let's go for term by term evaluation. Integrating sin theta we get minus cos 2 theta by 2 Already we have sine 2 theta by 2, so it becomes cos 2 theta by 4, and 1 minus cos 2 theta by 2 split into two terms, 1 by 2 minus cos 2 theta by 2. Integrating 1 by 2 we get theta by 2. Integrating cos 2 theta by 2 we have minus sin 2 theta by 4, and integrating 1 we have t theta, and the limits 0 to pi. So applying the limits, we know cos 2 pi, substituting the upper limit, cos 2 pi is 1, therefore 1 by 4, and the second term it becomes pi by 2, and in the third term we have sin pi, sin 2 pi which is 0, and in the fourth term theta equal to pi, minus, we give the lower limit, we know cos 0 is 1, and then giving theta 0 in place of theta, all other terms become 0, and here we have plus 1 by 4 minus 1 by 4 get cancelled, so the rest of the terms is just pi by 2 plus pi, which add up to give 3 pi by 2. Now let's do the integration, the next part of the integration, that is along C2. C2 is the lower part of the circle, that is the lower semicircle. So the lower semicircle spreads from the third quadrant to fourth quadrant, where theta varies from pi to 2 pi. Let's scroll back to check this angle. Here we can see that from BDA, along BDA we have the third and fourth quadrants included, so theta varies from pi to 2 pi, and plugging in all the substitutions, that is changing into polar coordinates, same as the previous integral, we can directly, only the limits are going to change. So integral over C2 x minus 2y dx plus x dy, it should be x minus 2y, mistake over here, let's leave it. I am now plugging in the trigonometric, that is polar coordinates, converting into polar coordinates, we give x is equal to cos theta, y is equal to sin theta, dx is minus sin theta d theta, and dy is cos theta d theta. So plugging in all these substitutions and opening up the brackets and applying the identity as in the previous integral, let us write down the step directly. So it is because we have to repeat the previous integral as such. So we have same as in the previous case, minus sin 2 theta by 2 plus sin square theta plus 1 d theta. Now the sin square theta cannot be evaluated directly, so we can go for the identity 1 minus cos 2 theta by 2, which on integration gives theta by 2 minus cos 2 theta sin 2 theta by 4 plus theta between the limits pi to 2 pi. Now applying the upper limit 2 pi, we have cos 4 pi which is 1, so it is 1 by 4 plus 2 pi by 2, it becomes pi, sin 4 pi is 0 plus 2 pi minus, apply the lower limits, cos 2 pi which is again 1 by 4, theta is pi, therefore pi by 2, sin 2 pi 0, again theta equal to pi. Now plus 1 by 4 minus 1 by 4 get cancelled, and plus pi minus pi get cancelled, so the rest of the terms 2 pi minus pi by 2, which is again 3 pi by 2. So summing up, integral, closed integral over C, x minus 2y dx plus y dx dy, that is equal to integral along C1 and plus integral along C2, which is nothing but 3 pi by 2 plus 3 pi by 2, which is 3 pi. Now let's go for the evaluation of the right hand side. So what's the thing we have in the RHS? Along RHS we have double integral over R dou f2 by dou x, sorry, dou x minus dou f1 by dou y dx dy, where f1 is x minus 2y, so dou f1 by dou y is minus 2, f2 of x comma y is x, so dou f2 by dou x, it is equal to 1. So double integral over R dou f2 by dou x minus dou f1 by dou y dx dy is equal to double integral over R dou f2 by dou x is 1 minus of minus 2 dx dy. So it is 3 times double integral over R dx dy. And we know in the last semester also we studied in the applications of multiple integral, double integral over R dx dy gives the area of the region R. Here the region R is the circle x square plus y square equal to 1, that is the circle centered at origin and radius 1. So 3 times the area of the region R is nothing but area of the unit circle. So this 3 pi r squared, radius is 1, so 3 pi 1 squared, which is 3 pi. And already we have got the left hand side to be 3 pi. Now the right hand side is also 3 pi. Therefore we have verified closed integral over C f1 of x comma y dx plus f2 of x comma y dy is equal to double integral over R dou f2 by dou x minus dou f1 by dou y dx dy. Hence we have verified the Green's theorem. Okay, we will discuss more problems in the next videos.